All right, so we're going to look at a couple of things today. We're going to look at connecting infinite limits and vertical asymptotes, and we're going to look at limits at infinity and horizontal asymptotes. All right, so our goal is to be able to interpret the behavior of a function using limits involving infinity. So we're going to start off just by reviewing a little bit here. Going back to pre-calc, algebra 2, the definition of a vertical asymptote, it says if f of x approaches infinity or negative infinity as x approaches c from the right or left, then the line x equals c is a vertical asymptote of the graph of f. Let's take a look at how that works. What is an example of that? So here in example 1, I've got this function, and if I wanted to graph this function, one of the things I would want to do is see if there's any holes, any vertical asymptotes. So I'm going to take my function and I'm going to factor it first, f of x, and we're going to get x plus 4 times x minus 2. Oops. Said it and didn't write it. X minus 2. And the denominator is x plus 4 times x minus 3. And you can see right away that we get a couple of factors that cancel. So I know that I have a hole at x equals negative 4. The x minus 3 that's left over tells me that I have a vertical asymptote at x equals positive 3. Okay, a vertical asymptote comes from a factor that does not cancel. So if we were to graph this, it's going to look something like this. We'd have our vertical asymptote over here at 3. So we can toss that in there. We'll just say x equals 3. And if you were to plot some points and that kind of thing, it turns out that this graph does something along these lines. It comes down like this on the left, and it comes up like this on the right. Something like that. Not a great drawing, I know, but it would look something like that. And now in part B, we want to evaluate the limit as x goes to 3 from the negative side. So on the negative side, I'm going to follow my graph down this way towards negative 3. But that graph ends up going down to negative infinity. So the limit would be negative infinity, or you could say does not exist. All right? And then it asks for the limit going the other direction. The limit as x approaches 3 from the positive side of f of x. Well, now you can see on the positive side, on the right side, the graph is going to go up towards positive infinity, or does not exist. So what is the limit as x approaches 3? Well, remember, a limit is a y value. It's a number, so we would have to say that this limit does not exist. So that's one way to look at a vertical asymptote and a limit when you have a vertical asymptote. Take a look at this next one. Same type of situation, but I don't have to factor first. I know that this function has a vertical asymptote at x equals 3. However, I don't know what's happening on the positive side. That's what this one's asking for. The limit as x goes to 3 from the positive side of this function. So if there's a vertical asymptote at 3 and I want to go to the positive side, I'm going to let x equal, let's say, 3.001, and I'm going to plug it into the function. So plugging in, I would say 1 minus 3.001 all over 3.001 minus 3. Now, I don't care what's going on the top, but if you were to subtract here, you would get negative 2.999 over 0.001. Well, let's bump each of the decimals in the numerator and denominator over to the right 3 times. So basically multiplying by 1,000 here. So I would have negative 2.999 over 1. What does that mean? That means that this graph is heading in a negative direction as x gets closer and closer to 3 from the positive side. So I could say as x approaches 3 from the positive side, f of x approaches negative infinity. So the limit here, so we would say that the limit as x approaches 3 from the positive side of f of x is negative infinity, or again, you could say does not exist. And we can do the same thing on part B here. So we've got a function again. The bottom can be factored, so I'm going to go ahead and factor this. This is the limit as x approaches 1 of x minus 3 over x minus 1 times another x minus 1. So no factors that cancel, but we can definitely see a vertical asymptote at 1. Vertical asymptote, x equals 1. Okay, I want to find the limit as x approaches 1. Now here's the thing. Because there's a vertical asymptote here, I really don't care what this limit is. This limit does not exist. And the way I know that is because if I were to graph this, I know there's a vertical asymptote here. So my graph is either going up like this at 1, possibly, maybe it's going down like this at 1, something like that, but I know it has to because of the vertical asymptote, so I could write right away that the limit does not exist. If I wanted to check that limit to see if it's positive or negative infinity, then I would have to do something like, let's see, let's do the limit, let's say x approaches 1 from the positive side. So I'm going big again here. And when I say the positive side, we need to go to like 1.001. So I'm going to let x equal 1.001. And I'm going to go ahead and plug that in. So here we go. 1.001 minus 3 over 1.001 minus 1 times another 1.001 minus 1. If you do some math on the top, you get negative 1.999 over 0.001 squared. Now, I've got the same situation as I did in the previous problem. The top has 3 decimals. The bottom's actually going to have 6 decimals. Because once you square this, you're going to end up 0.00001. Excuse me, it's going to have 5 decimals. All right, so I know that if I bump the decimals over, this thing has to be going to negative infinity. So I would say negative infinity on this side, and I can do the same thing on the other side. I can come back and say x approaches 1 from the negative side, so I'll let x equal, I don't know, let's do 0.999. How's that? Here we go. So we got 0.999 minus 3 over 0.999 minus 1. And actually, I'm going to cheat this time because that's really just squared, right? There's 2 of them, so it's squared. And so I end up with negative 2.001 over, and I'm going to negative 0.001, again, squared. So that goes to negative infinity as well. So if you were asked the question, does it go towards positive or negative infinity, you could definitely say negative infinity. But if it just says, what is the limit as x approaches 1 of f of x, call f of x that function up there, this does not exist. All right, a little bit of pre-calc review there, along with some new stuff on the limits. All right, so we have limits that go to infinity. So like we saw in this last one, I was asking for the limit as x approaches 1 or x approaches 3, whatever it is, and those limits went to positive infinity or to negative infinity. Now we're going to look at horizontal asymptotes and infinite limits. So ways to find infinite limits, okay? Plug in the values or look at the graph. The definition of a horizontal asymptote is the limit as x approaches either positive or negative infinity. So take a look at example 1. It says find each limit using the t-tables given. Here's my function f, and they want me to plug in all these values here. So if I plug them in, if I plug in 10, I get 10 minus 2 in the denominator, which is 8. This is 3/8. Okay, big deal. So I plug in 100 in the denominator. Now I have 98 in the denominator. That's 3 over 98. I plug in 1,000. I get 998 in the denominator, but I still have 3 in the top, right? 3 over 998. Maybe you're starting to see a pattern here. I plug in 10,000 and I get 3 over 9,998. So the denominator is getting bigger and bigger and bigger, but the numerator stays the same. When that happens, as x gets bigger, okay, I'm going to say this one way, as x gets bigger, f of x gets smaller and approaches zero. If you take out your calculator and you start to plug in those fractions into your calculator for a decimal value, these decimal values are getting closer and closer to zero. Now, if you look at your function, when we took pre-calculus or algebra 2, we didn't care about the minus 2 back here. When we looked at a rational function and we were looking at, okay, where is my horizontal asymptote on this rational function? All we did is we looked at the lead term in the numerator and the lead term in the denominator. We didn't care about that other stuff. So if I look at this, I want to look at this as 3 over x. Those are the lead terms in the numerator and denominator. And as x gets bigger, 3 over x goes to 0 as x goes to infinity. As x gets bigger, that value is going to get closer and closer to 0. This is true, if you remember again from pre-calc, this is true whenever the denominator grows faster than the numerator. So how does the denominator grow faster? This happens when the degree of the denominator is greater than the degree of the numerator. So if you go back and look at this function, the degree of the denominator is 1 because that's x to the first, and technically the degree of the numerator is 0 because 3x to the 0 power is still 3, because x to the 0 is 1 unless x is 0. Okay? So we really don't have to worry about that. All we really need to know is what's the degree of the numerator and the degree of the denominator. So when the degree of the denominator is greater than the degree of the numerator, then the horizontal asymptote will always be 0. So the horizontal asymptote is y equals 0. Now you go to the next one. It's a little bit different. It's x plus 3 over x minus 2. So again, if I plug in 10 into the function, I'll do the first one. I get 10 plus 3, which is 13 on the top. 10 minus 2 on the bottom is 8, so I get 13 over 8. And then I do 100. 100 plus 3 is 103. The denominator is 100 minus 2, which is 98. And I keep doing that. And this time, when I do 1,000, I get 1,003 over 998. And then I get 10,003 over 9,998. Now 13/8, that's bigger, that's much bigger than 1. That's like over 1.5 right there. But as you look at some of these other numbers, 103 over 98, that's barely over 1. 1,003 over 998, that's even closer to 1. 10,003 over 9,998 is even closer to 1. So as x gets bigger here, again, go back to pre-calc, Look at the lead term in the numerator and the lead term in the denominator. If I look at those, I have x over x, which is equal to 1. Even though there's a plus 3 on the top and a minus 2 on the bottom, as x gets bigger, as x goes towards infinity, the top and the bottom will eventually become so close to each other that the limit is equal to 1. Now, the limit isn't always equal to 1, but I can divide these lead terms. This is true whenever the numerator grows just as fast as the denominator. So if this is x over x, I'm going to get 1. Now, contrast that. Let me give you another function here real quick. We'll take a look at this one. F of x equals 4x squared minus 7 over x squared plus x. Just look at the lead terms. Okay? My lead terms are 4x squared and x squared. So the x's grow at exactly the same rate. They grow just as fast as each other, but the 4 always remains on top, and so this would have a horizontal asymptote at y equals 4. This happens when the degree of the numerator is equal to the degree of the denominator. All right, and again, these are all pre-calc rules here that we're reviewing. And the last one here, you can almost visualize what's going on here. If you're thinking about the degree of the numerator and the degree of the denominator, you see that the degree of the numerator is much bigger. And watch what happens when we start plugging in our values. I plug in 10 to the top, to the numerator, I get 103. 10 in the bottom, I get 8. I plug in 100 to the numerator, I get 10,003 over 98. So now the numerator is growing really, really, really fast. Look at the next one. 100,003 over 998. The numerator is growing much, much faster. So these numbers are getting bigger and bigger and bigger as x gets bigger and bigger and bigger and bigger. So this limit has to be infinity. And again, I'll go back to what's the degree of the lead term? That's x squared divided by x, which cancels out one of the x's and leaves me with x all by itself. So as x gets bigger and bigger and bigger, this value goes to infinity. This is true whenever the numerator grows faster than the denominator. And that happens when the degree of the numerator is greater than the degree of the denominator. Okay, so now let's take a look at some of these using those rules. Letter A. Okay, the limit as x goes to negative infinity. Now, look at the lead two terms here. Okay, look at the lead two terms here. So I'm going to look at this. Look at this as the square root of x squared over x. Those are my lead terms. Square root of x squared over x. We don't care about plus 3. We don't care about minus 2, because as x gets bigger or smaller, the plus 3 and the minus 2 don't make a difference. So, now, if you look at the denominator, as x goes to negative infinity, the denominator is going to stay negative. It's just going to get really big, but it's going to stay negative. The numerator, as x goes to negative infinity, like if you plug in negative 10, you square negative 10, that's 100, and then you square root 100, that's positive 10. So because of the squared in here, the top, the numerator, is going to stay positive. One of the ways to look at the square root of x squared okay, the square root of x squared, like we just talked about. If you plug any number in for x, and then you square it, and then you square root it, you will always get a positive x, which means you always get the absolute value of x. So if I'm looking at the lead terms here, I know that the numerator is always going to be positive x, absolute value. The denominator is still x. So imagine for just a minute, okay? Imagine for just a minute that we could actually plug in negative infinity. So I put negative infinity there. I put negative infinity there. The top one becomes positive. The bottom one becomes negative, or stays negative, and the answer is -1. Okay? So the answer is -1 because the top stays positive and the bottom stays negative. Now, you probably don't want to write this on our exam or AP test because infinity over infinity, I guess it wouldn't be bad to put it there, but I would not put equal signs in there. Okay, I wouldn't put the equal signs in there for sure. So that's going to equal -1. So we have a horizontal asymptote at -1. All right, let's look at the next one. Let's see here. Letter B. Oh, look at this one. Now again, I'm gonna do some stuff here that some teachers may frown on, but when you see a limit, the whole idea is plug in the number. I don't have a number, I have infinity. Okay, so again, imagine, let's just plug in a couple of numbers here to see what's going on here. Okay, so if I plug in 1, I get out 4. If I plug in 100, I get out 103. If I plug in 1,000, I get out 1,003. So as x is increasing, my y values are increasing. And imagine if I just did this. What if I plugged in infinity? Infinity plus 3 is infinity. So this limit is going to infinity. Now, what's another way to look at this? This is a linear function in here. This is y equals x plus 3. If I were to graph that, it would look something like this. As x goes towards infinity, my y values are going towards infinity as well. So the limit is infinity, or again, does not exist. Now you could do the same thing with negative numbers. Start plugging in negative numbers and you'll see it, the function, decrease as x goes to negative infinity. If you look at the graph, as x goes to negative infinity to the left, the y values are going down towards negative infinity, so this would be negative infinity. Same thing with letter D. It's a parabola. How do I know that? Because it's x squared plus 1.3. So in this case, again, if you plug in infinity, infinity squared is infinity. And we can't ever reach infinity, but that's what can go through your mind here. Infinity is not a number, but if you plug in very large numbers and square them, they just get bigger and bigger and bigger. So this thing has to be going towards infinity. The other way to look at it, because it's a parabola, it's got a y-intercept at 1.3, and because it's a parabola, you can see that both the right side, as x goes to infinity, y goes to infinity. On the negative side, as x goes to negative infinity, y goes to infinity as well. And these functions should be familiar. And then we get to the next one. Now I'm going to go back to pre-calc again here for just a minute. Look at the degree of the numerator and the lead term in the numerator, lead term in the denominator. All I have to do is divide those out. X squared over 3x squared. The x squareds are going to cancel and leave me with 1/3. So f of x has a horizontal asymptote. We're going to call that HA, horizontal asymptote at y equals 1/3. So if we were to graph that on a graphing calculator, we should be able to see that. Now you take the same exact function and you go to negative infinity this time. So last time we went to positive infinity, this time we're going to negative infinity. So I'm still looking at x squared over 3x squared. But now we're plugging in larger and larger negative numbers, but we're going to square them right away. So they're both going to go positive and positive anyway. The top's going to stay positive, the bottom's going to stay positive, and we end up with 1/3 again. Same thing as before. Letter H. The limit as x goes to positive infinity of this rational function. So again, I'm going to take out the lead term in the numerator and the denominator here. So I'm looking at this as x over 19x squared. So right away I'm seeing that the numerator is going to grow much slower than the denominator. So if the denominator grows faster, this function here will go to 0. So the limit is 0, which also means the horizontal asymptote is y equals 0. And then you go to the next one and you're thinking, oh, this is easy, right? I plug in negative infinity, that's an infinity or negative infinity, but here's the deal. This is e to the x. This is e to the x. So if I'm gonna, now, and again, just think about it like this. E to a negative exponent. Let's just call it negative infinity for a minute. First of all, the negative exponent says to flip it over. So I would do 1 over e to the positive infinity. E to the positive infinity. So e to the first is 2.7 something. E to the second's going to, I think it's, I don't know, 8 point something. This thing is just going to grow outrageously huge. E to the infinity is just going to get really, really big. But there's a 1 in the numerator, which isn't growing at all. So this fraction goes to 0. As x gets bigger, e to the negative, or excuse me, as x gets smaller, because we're going towards negative infinity, right? As x approaches negative infinity, this part of the fraction will approach 0. Why do I need to know that? Well, check it out. If the top, if e to the x approaches 0, then I get 0 take away 6 in the numerator. I have the same situation in the denominator. E to the negative infinity is 0 minus 4. And so I end up with negative 6 over negative 4, which is positive 3/2. Okay, so if it's got e to the x, you got to be careful here. I would encourage you to turn off the video and try these last two. There's a little bit of a trick to them, but you could try them and see. I'm going to look at the lead coefficients in the numerator and denominator. So I'm going back to pre-calc x over the square root of 3x squared. So I look at it like this, I rewrite it so I can see what's going on, and then I remember something about the square root of x squared. Remember, we talked about that earlier. So I know that the square root of x squared is really just the absolute value of x. Now, the biggest mistake that happens here is when people simplify the x squared, they take the 3 out too. But the 3 can't come out because the square root of 3 is not 3. The square root of 3 is the square root of 3. There's no whole number value for that. So when I look at this limit here, I can look at the denominator as root 3 times the absolute value of x. Now, if you look back at your limit, this is as x goes to positive infinity. So the top is going to be positive. The bottom is going to stay positive because of the absolute value anyway. So these guys, the x's, actually cancel each other out and leave me with an asymptote, a horizontal asymptote of 1 over the square root of 3. Now look at the next one. The limit as x goes to negative infinity. Here's my lead terms again. A little bit different here, but I'm going to look at this as 3x. The denominator is the square root of x squared, so remember that's the absolute value of x. So as x goes to negative infinity, the top goes negative, but the bottom stays positive. The x's would cancel, so the 3 is going to become negative. Have fun with the homework.